Hi Year 12, this is the mark scheme for pages 13 to 19. Apologies for the quality of the scan, but hopefully it's the answers that you're interested in. I would strongly recommend you listen carefully and it should give you some tips and some exam technique. So start with the first question, which you had to draw the isomers of butanol. One has been drawn for you and you had to complete the table. So the best thing to do here is to be as systematic as you can be. So we've got 4 in a row with 1 OH. So you want to continue that with 4 in a row, but rather than putting the OH on the end carbon, we want to put the OH on the second carbon, and then obviously you'd need to fill up with all of your H's. The next one to do, there's no other places to put the OH, because if you put it in any of the other positions you'd be repeating one of those two. So the next one is to cut the carbon chain by 1, making it 3 in length, and then you've got the methyl group, which has to come off the central one or it's not a branch at all. And then you've got 2 possibilities for where you can place the OH. You can either place it on the main chain in the central position, like so, with all the H's, again making sure that you draw all the H's, apologies for the slight overlap. And then the last one is also 3 in a row, with the methyl group coming off the central position, but then you need to place your OH on any of these positions. So I'm going to put it down here, and any of those 9 positions on these end groups here would give an equivalent structure. They're then talking about oxidising the butanol. So obviously we've got a primary alcohol that we're oxidising, and it's talking about using acidified potassium dichromate to form a carboxylic acid. So the colour change that you would see for dichromate, remember, is orange to green. 1 mark for both words in this case. Write a balanced equation for the oxidation of butanol. Now, because it's saying butanol, ideally you should be using the structural formula for the examiner. So placing your OH on the end position. So CH3, CH2, CH2, OH. In fact, I've just realised I need another CH2, OH, apologies. So CH3, CH2, CH2, CH2OH, 4 carbons in a row. They would allow C4H9OH, that is also okay. You then need the square bracket oxygen and the product, carboxylic acid. Obviously you again need to show that that would be the straight chain. So CH3, 2 CH2 groups, COOH and H2O is there. Now if you count up, so you need the H2O, otherwise you're short on hydrogens, and then if you count up your oxygens, you will require 2 oxygens here from the oxidising agent. So you put the balancing number in front. That is marked 1 mark for the carboxylic acid formula, which needs to show it is straight chain ideally. You have to identify which of the isomers could be oxidised to form a carboxylic acid. That has to be the one that is the 2-methyl-propanol. It has to be the primary alcohol. So the 2-methyl-propanol that I have drawn is this one here. So isomer 3 of the ones I've drawn, you've got 3 in a row with the OH on the 1 position and the methyl group coming off the 2nd position. Up and to the right, I can't remember whether or not you could see this part of the question. It's not essential information, but it did say butanol reacts with hot concentrated sulfuric acid to form compound B. So that should be a dehydration reaction, but you can pick it up from this information. Compound B has an empirical formula of CH2, relative formula mass 56, and you had to use that information to deduce the compound B formula, and you had to show your working. So the working mark is going to be for the empirical formula mass of CH2, which adds up to be 14, 12 for the carbon and 2 lots of 1. And of course you should be able to see the multiple required to take 14 up to your 56 is a multiple of 4. You don't need to write this bit down, but that was what would give 56. And so our molecular formula for the second mark would be 4 lots of that CH2, so giving us C4H8. The balanced equation to show the conversion of butanol, so again they have said butanol, but for speed I'm going to say C4H9OH, ideally using the same structural formula as over here. However, I don't think in this case they penalised for that, and that forms C4H8, which we've just worked out, plus we have lost the water because it is actually a dehydration reaction. Now, the other isomer that would also react with hot concentrated acid to form compound B. So if you are forming compound B, C4H8, from butanol, that is going to actually be removing the OH in the adjacent hydrogen and putting your double bond in there. So they are asking you which one of these other isomers would form that same but1ene molecule when you take out the water. So it has to be the butanol. So whichever you've drawn as butanol, in my case this one here, showing you'd remove that one there, and that would that would take this one here and would put in our double bond there, apologies. It can also form our but2ene, but also but1ene, which is the question. So the ester was formed by reacting ethanoic acid with butanol. They gave you the equation. Notice they've also given you the molecular mass of 116, which you'll need in the calculation in a moment. The catalyst for that reaction, you need to recall, that is H2SO4. It is actually concentrated, but I'll put that in brackets because it wasn't required for this particular mark scheme. Now they now say they need 6.96 grams of the ester produced from 0.100 moles of butanol. Calculate the number of moles of ester formed. So our number of moles of our ester, remember, mass over molar mass. So our mass 6.96 and our molar mass 116, and so our answer 0.06 moles. And obviously to be totally correct, you'd have a couple of trailing zeros there for the moles. They will accept that answer too. Finally, on this page here, this question, calculate the percentage yield. They will allow you error carried forward here if you didn't get 0.06, but it's that number of moles that you've formed. You've also been told the number of moles that was used of butanol, and because butanol is going to react in a 1:1 mole ratio, that is also the same as the number of moles of product ester you would expect to form. And so what you got out of the total times 100 gives you your percentage, and the answer of course is 60%. Okay, so let's move on to our next page. So our next page, another calculation. They gave you the percentages, carbon, hydrogen and oxygen. So what you should be looking to do is use columns and you should be showing all your working, although not every bit of working will pick you up credit. You're looking for the percentage, which can act like a mass over the molar mass. So for hydrogen, 13.3 over 1, oxygen, 26.7 over 16. It's this next answer that will get you your first marking point. 5 to 13.3 to 1.67. So there's our first marking point. And then if you divide by the smallest, that gives you 3 to 8 to 1. So they'll accept that ratio for a second mark, or actually writing out the formula C3H8O. Remember, you shouldn't give away anything about that formula. Even though they tell you it's an alcohol, the empirical formula should be written with the atoms separately. So there's your second mark, it's one of those two answers. The next one, the relative formula mass was told to be 60. Show that this agrees with the molecular formula. So they've told you the molecular formula is C3H8O, and they've asked you to prove that that matches the working. So what you'll need to do is prove that 3 lots of your carbon at 12 plus 8 lots of your hydrogen of 1 plus your oxygen of 16 gives you an answer of 60, which of course matches with the molecular mass. You have to show your working if you want to get that mark. Now compound A, which remember we've now worked out, C3H8O, 2 possible isomers that are both alcohols. So it has to have an OH group, because you've only got 3 carbons, so there's no branching possible. So they're both going to be based along a 3 carbon chain, and the difference between those is where you place that OH. So you can either place it in the 1 position on any of these ends, and all of those filled up with H's. You do need to have those. And then the other option would be our propan-2-ol, again with H's in all of those other positions to finish that off. 1 mark for each of those structures, doesn't matter which way around you put them. So they reflux with an excess of oxidising agent. So the excess of oxidising agent is going to tell you something about the type of product that we are going to get, which we come on to over here. So there's a clue already in the question about what we're going to form. The suitable oxidising agent, there's various ways you can give that. Dichromate. Now it is actually acidified dichromate, but in this particular mark scheme you don't need to say the acidified. I'd be careful because in others you might well need to say that. You can use words, you can use formula or ionic formulae, but of course the formula must be correct. Dichromate is Cr2O72-. On other mark schemes you might need to say /H+. And there is an alternative. Of course, if you don't use dichromate, you can use manganate 7, MnO4-. The colour change in the next part, if you use dichromate, which is the most popular one, would be orange to green. This time that's worth 2 marks, so 1 mark for each colour. If you chose manganate, that would be purple to colourless, would be what they were looking for there for the 2 marks. And explain what is meant by the term reflux. Remember, reflux is where you've got that vertical Liebig condenser, allowing it to continuously heat without losing your reagent or product, and that needs to be continuous evaporation and condensation. Okay, on to our infrared spectra. So you're given that infrared spectrum of our compound B, and you're asked to identify the absorption responsible for X. So what they're asking you there is what part of the molecule, what bonded section of the molecule is responsible for that peak. And the answer to that, if you use your data sheet, because it's way up in around the 3000 mark and it's really broad across there, the absorption peak is for an OH. You can either say OH, or you could say alcohol, or you could say hydroxyl. Any of those would pick you up the mark in this case. The absorption responsible for Y, which is quite a sharp peak there, is the C double bond O absorption, which you should be getting familiar with now from your work on infrared. The alternative you can say there is a carbonyl group. They will accept that. And because piecing these two pieces of information together, along with the fact that they did say it was reflux with an excess of oxidizing agent, you can then say that that is a carboxylic acid, or you could use the functional group COOH. Either of those will pick you up that mark. Now, using your answer to D, explain which of the isomers from B, so which of these two isomers must be our compound A. Well, that must be our propanol, because the only one which can fully oxidise to a carboxylic acid is a primary alcohol. So you do need to explain the answer, so you need to say that it's oxidised to a carboxylic acid. Finally, on this question, writing a balanced equation for the oxidation of compound A to form compound B. Now, just in case you've made an error on the previous one, they, on the mark scheme, just write C3H8O. It is, of course, the structural formula for propanol would be the ideal answer, but they wouldn't penalise you again if you'd used propanol, so that's why I've written C3H8O. Oxidising agent, O in square brackets, and our product ideally will show our formation of our carboxylic acid, CH3, CH2, COOH. In order to balance, we at the moment have only got 6 hydrogens, so we need some more, so we need our water, and then we need to, for our second mark, we would need to balance our oxygens from the oxidising agent, like so, 1 mark for the formulae and 1 mark for the complete balanced equation. Okay, on to our next question. So, question 3, an organic compound was analysed and found to have a relative formula mass of 62 and a composition 38.7 carbon, hydrogen 9.7 and oxygen 51.6. So again, we're using our columns C, H and O. Ideally, you should show your full working, 38.7 over 12, so this is our mass over molar mass, 9.7 over 1 and 51.6 over 16. But the mark scheme is looking for the answer to that, which is in moles, 3.2, 9.7 and 3.2. It's fine if you've written more accurate answers than that. That's just what the mark scheme says, they'll accept. And then your second mark, you need to take it down to the simplest ratio, divide by the smallest, 1 to 3 to 1. But for this one, you do need to make sure, as with all of them, you should do this, just in case, CH3O is your second mark. So you've got 1 mark for this row here and 1 mark for your final answer. It then says to deduce the molecular formula of compound A. Now it is only worth 1 mark, so they probably accept, in most cases, looking to accept your final answer. It's always worth putting your working in, just in case they say you need to have done both for that 1 mark. So the empirical formula mass, you've got carbon, which is 12, 3 lots of 1, and your 16 gives 31. And of course the question said that the molecular mass was 62. So the multiple is 2. So your answer for your 1 mark is C2H6O2. Now, the infrared spectrum of compound A in absorption between 3230 and 3550, the functional group indicated by this absorption is the alcohol. In this particular question, they wanted the functional group, so we're looking for the name. they didn't accept in this particular instance OH as that. Okay, now some of you might have got tripped up by this next one, so let's look at this carefully. We've got a molecule of compound A will react with an excess of ethanoic acid, CH3COOH, to produce the compound below. Deduce the identity of compound A. So this is forming what you should recognise as an ester. You've got actually two ester groups, COO there and a COO there. Now you should know that an ester is formed from an alcohol plus a carboxylic acid, and when it forms, if you remember, you join in the centre of that ester link. So what I'm going to do is I'm going to work backwards. I'm going to split it. Both of those ester links need to be split. Now here is where you can see the CH3CO, and that is where the carboxylic acid came from with the OH on there. So if that was the one with the OH on it, then that means this was the alcohol. So that needed to put an H back on there. Same over here. This had our OH on it from a carboxylic acid, and so this one over here would be an alcohol. And so what you've got there is you've got the ethane chain with two OH groups, one on either end. Do make sure, if you're drawing it like this, that you are binding it through the oxygens and that we've not got one of them back to front. You can either draw it out like that, or you can name it, which would be ethan 1,2-diol. And suggest why compound A has an unusually high boiling point. That is because you've got two OHs, you've actually got lots of hydrogen bonds. You don't need to go into any more detail than that, so whatever you've written, look for whether you've talked about hydrogen bonding. Okay, on to our next one. So the structure of linalool, apologies, my hole punch, because I had to scan in my hole punched sheet. My linalool had a CH3 on there, you should be able to see that on yours. And they've given you a structural formula and a skeletal formula, and that's going to be useful throughout the question. You can see where you can pick up some clues. So the functional group identity, first of all, we've got two functional groups. You can either say alkene, or you could say C double bond C. So you've got a couple of those in there. And you've also got our OH there. So you could say OH, or you could say alcohol, or they would accept hydroxyl as well. Any of those ways to pick up those two. You cannot, remember, use an alkane as a functional group, because as soon as you've got anything else in there, that is going to supersede that. So linalool reacts with hydrogen in the presence of a catalyst to produce a fully saturated compound A. So the term saturated, you can either say contains no double bonds, or you could say no multiple bonds, or you could say contains single bonds only. Any of those descriptors. The catalyst to hydrogenate, reaction with hydrogen. The main one we've talked about is nickel. You can also use platinum, you can also use palladium, and you can also use rhodium. I'd probably expect you to be picking one of those first two. Complete the reaction scheme below. So we've got our linalool shown in the structural formula. So you'd want to emulate that in our compound A product. And we are adding excess hydrogen, suitable catalyst. So we want to correctly add our hydrogen across each of those double bonds. And you've got to be careful as you do it. So work your way along, CH3 on the end. Emulate this structure, then you're less likely to make a mistake. Now, where you had the double bonds, you want to now take that double bond out, and because you've taken the double bond out, you're going to need to put something in its place, the hydrogen, so you need an H on there, and you need to have two H's on the bottom. And then up here, from this structure, we've got our CH2. Notice they are drawing it accurately through the carbons to be correct. Then we get up to here, we've got our CH3 and our OH, none of that is changing. And then we go down to our second double bond, where again we need to get rid of that double bond. Now, they had CH, that's got to have another H on there, CH2, and CH2 there has to become a CH3. So each of the double bonds has to go and have to make sure that you have correctly placed an additional H in 1, 2, 3, 4 places. You need an extra H. Everything else in the structure needs to be the same. So 1 mark for the correct addition across each of those C double bond Cs. So if you only did one of them correctly, if you made a mistake on one or you forgot to do them both, then you would drop one of the marks. Now it's asking you to draw the skeletal formula of A. So here we've got the clue at the top. We've got our skeletal formula of our original linalool. All we need to do is copy that, but not put in our double bonds. So again, we want to completely emulate that, but all that's missing is this double bond here and that double bond there, and they've been exchanged for single bonds. Everything else, you use that as a clue to what we've got. On to our next page. So we've got a question about menthol. So again, we've got two structures shown which can be useful. We've got our structural formula and we've got our skeletal formula. First thing is we're asked for the molecular formula of menthol. Remember, the molecular formula needs to show no detail. All you need to do is use that left-hand structure here to count up very carefully, count up how many carbons, hydrogens, oxygens. The answer is C10H20O. When it's such a large structure, always worth a quick double check on that one. If you've given away any structure at all, if you've put any OHs or anything in there, unfortunately you will lose the mark. Now, the functional group present in menthol that's going to distinguish it as primary, secondary or tertiary is of course our alcohol or OH group, or you can use hydroxyl again, so any of those three. And in this particular case, we are classifying that as a secondary alcohol. If you look at the OH up here and look at the carbon attached to the OH, you've got one H and then you've got two, effectively what are R groups. Obviously they join round, but they are both R groups, they're not H's. So we've got two R groups, so that means it's secondary. Now, the next question is asking you to react with hot concentrated sulfuric acid. You should recognise that that is the dehydration reaction. So we want to remove water from that molecule. And we can form two isomeric alkenes. So we know we're looking for an alkene. And what we want to do, the reason there are two forming is, remember when we went through this on one of my previous videos, I'm just going to put in the hydrogens on the adjacent carbons to that OH. So we've got the carbon here with our OH. There is of course a hydrogen on there as well, but I'm not going to need to show that one. And there are two here and there's one here. And what happens is the OH is removed either with the adjacent one on that side. Now if you remove it with that one, you're going to have a very similar structure, but where you've removed the water, that's going to give us our alkene. Remember it said we're going to form alkenes, And the other one is if you remove the OH with the H adjacent on the other side of the molecule, or other side of the OH, and that would give us our, again, very similar looking molecule, so most of it the same, but our double bond now is between those two carbons. So those are our two isomeric alkenes. Remember, when you're reacting, it's only the functional group and the small area around it that is going to change. So over here, it's saying menthol. So back to our reaction with menthol, reacted with ethanoic acid. So just in this space here, I'm going to show you. If I put our menthol here, remember on an exam paper, you can always use these extra spaces to work things out. Now, we're going to react our alcohol from our menthol with our carboxylic acid, ethanoic acid. And I'm going to place that so that my OH is there next to that, and there's my carboxylic acid. So ethanoic acid, 2 carbons, and my carboxylic acid, and I've placed it so that my carboxylic acid is next to my alcohol, because remember what happens in that is the water is removed there. It is actually, remember, the OH from the carboxylic acid and the H from the alcohol, and if you cut that out and join those two together, that is your product. So what we are looking for our answer, so this part of the structure needs to be the same. Then we've got, coming off there, we've got our O from the OH, and then that then joins to the carbon of the carboxylic acid group, and then we've got our CH3. So the 2 marks there, 1 mark is available for the Ester group, there, so that's 1 mark, and showing the CH3 bonded via the COO to the ring, and the rest of the structure then makes up your 2nd mark. Okay, on to our next page. Working through the questions. So we've got a question here. It's quite a lot of writing at the beginning. Obviously you can read that through for yourself. Apologies again for my hole punch that's knocked that out, but you should be able to see it on your script. And what you see is we've got an ester, that is COO, and then there was CH2 in that gap as well. So you've got a slightly branched ester over here. And it gives lots of information that you're going to need in the calculations going through. And it says, by referring to the experimental procedure above, so you do need to carefully read that through, state the role of the concentrated sulfuric acid. You should know for what is an esterification reaction forming an ester, that acid is there as a catalyst. It's still there at the end. You could alternatively say it's there to speed up the reaction. Again, we've got a similar question to earlier on. Refluxing, explanation, you should be getting used to this one now by now. Continuous, evaporation, and condensation. That's how it appears in the mark scheme every time. Continuous, evaporation, and condensation. Now, suggest which gas was responsible for the effervescence. Now, if you look back, it says the ester was washed repeatedly with aqueous sodium carbonate to remove any acid present until there was no more effervescence. So it's a reaction between the carbonate and the acid that's producing those bubbles. And that means the acid plus carbonate, of course, gives off carbon dioxide or CO2. Words or formulae is fine there. The equation for the ester, they've given you, so the ester formula drawn out again there, and you've got your alcohol and your carboxylic acid, and of course water as the second product. First question, you've got to read these questions carefully because they jump about a bit. Firstly, they ask you to calculate the relative molecular mass of CH3COOH. And so that is there are 2 carbons, so 2 lots of 12. There are a total of 4 hydrogens, 4 lots of 1, and 2 lots of oxygen at 16. The total, of course, of your answer is 60. Calculate how many moles of the ethanoic acid were used. So moles is mass over molar mass. So the mass, if you go back up in the paragraph, there we have it, 6 grams of ethanoic acid, and our molar mass of 60, and timesing, 6 over 60, mass over molar mass, answer 0.10 ideally, but again they will accept 0.1, and that answer is of course in moles, but they won't penalise for the unit there. Up over here, deduce the theoretical yield in moles of the ester formed. So of course 1 mole of ester forms from 1 mole of carboxylic acid. I'll just write it like that. So that means that if we have used 0.10 moles of acid, we would expect to form 0.10 moles of ester. So the theoretical yield, what we expect, should be the same as your answer to part 2. So on to part 4. They're saying we produced 7.8 grams. They're also telling you the molar mass, so saving your calculation, and asking you to calculate the number of moles of ester produced. So that's mass over molar mass, 7.8 over 130. Answer then 0.06. Ideally, probably putting in a trailing 0 there to give your 2 significant figures. Finally, for the calculation there, calculating the percentage yield of pure ester obtained. So they have said that, going back, we have used 0.06, they've produced, 0.06 was produced, and we were expecting our theoretical yield was 0.10. So our actual over expected, do not forget the times 100, that will give you 60%. Now on that one, they would accept error carried forward. You can replace whatever you got there with your answer for 4, and whatever you got there for your answer for part 2 can give you error carried forward if you don't get 60. Now again, you need to read very carefully here because they're jumping about, asking you to do different things. So we're looking at the ester E, which is formed from butanol, and it asks you to draw the displayed formula of butanol. So but means 4, 1ol means your OH is on an end. Now what you must not forget is they've asked for displayed, which means you need to show the bond between the O and the H here. Okay, so make sure you've got 4 carbons and that bond between the OH is shown. Draw the structure of the carboxylic acid used to produce E. So if you go back, here is the part that has come from our butanol. So this part here is giving us a massive clue for our carboxylic acid. So what we need is, we just need the structure, so you don't have to show the displayed formula, but it doesn't matter if you do. So there's the part that you can see there from the structure, and all we need to do is put our OH. We do not need to display any of these H's or the OH. We just need to show that it is the straight chain version of the 4-carbon carboxylic acid, so it's actually butanoic acid. Structural formula or displayed is also fine. Finally, onto the equation. That's only worth 1 mark, so you don't need, it's not too much to put it together. You've got all your information here. So you've got your carboxylic acid, CH3, CH2, CH2, COOH. You've got your butanol. Make sure I get enough carbons. So 4 carbons there. The ester, which you can just copy across, CH3, CH2, CH2, C, and you can cut that, you can just write COO if you wish, or you can draw it out, and then the 1, 2, just squeeze in there, CH2, CH3, apologies, just squeeze it on the page. And what you mustn't forget is the water. Okay, so you should have your carboxylic acid, your alcohol, your ester and your water, all correct for your 1 mark. They will, because it's only worth 1 mark, accept molecular formulae or formulae that don't detail, because obviously you might have made mistakes here in your original structures. So you can get away with C3H7 COOH, for example, or they'll even let you write the molecular formula, or here they will allow you C4H9OH because they've tested the fact that it's butanol up there. They'll even allow the ester to be written C8H16O2. Obviously you still need to have your water present for that last mark. Right, 2 questions to go. So this one here, again, based on a practical, you should be recognising, just for information, that this is the distillation apparatus. So you've got the Liebig coming out to the side. That's a clue potentially to some work later on. So again, lots of information about quantities and so on used. It asks you to identify the possible isomers of the alcohol C3H8O. That you have got propan-1ol and propan-2ol. You can of course draw out those structures. 1 mark for each of those. Now here we have an example where they've put in that complicated looking formula. You're going to need that for the ratio of moles. So the mass of sodium dichromate used was 39.3. Calculate how many moles of dichromate were used, and they tell you the molar mass is 262. So it is a straightforward mass over molar mass, 39.3 over 262. Answer 0.15, and they're probably looking ideally now for a trailing 0 and an answer, of course, in moles. They won't penalise, and they would accept 0.15 as well. Right, this next question, watch this because it does say the amount used was 0.300. Explain whether you've got the alcohol or the dichromate in excess. So you do need to do a little bit of thought. You cannot just make the point. If you look back at the ratio in the equation, you will see that the alcohol, you always require 3 times the quantity. It's a 3-to-1 ratio, and you've used 0.3 moles. So if it's a 3-to-1 ratio, then 0.300 moles of the alcohol reacts with 0.100 moles of dichromate. And therefore, if you've got 0.15, that means you've got more dichromate than our 0.10. So that means our dichromate is in excess. You cannot get the mark for just saying dichromate. You need to make this first point. It has to relate to the 3:1 ratio in the equation and therefore only needing to react with 0.1 moles of dichromate. The colour changes has come up earlier, orange to green. Again, this one is worth 2 marks, 1 for each colour. The student obtained 5.22 grams of the carbonyl compound. Calculate how many moles of C3H6O were produced in the experiment. So first marking point is the molar mass of C3H6O, which adds up to 58. 3 lots of 12, 6 and 16. And then your second marking point is for your mass over molar mass. 5.22 over 58, answer 0.09, and ideally another 0 in there for correct accuracy on figures. So 1 mark for that, 1 mark for that. I think they will accept 0.09 in this particular mark scheme. And then we have our final bit of the calculation. Theoretical yield 0.300. Calculate the percentage yield actually obtained. So what we actually obtained here, the actual moles produced was 0.090 over what we should have got, which is 0.300 times 100, answer 30%. Here you can replace that with whatever answer you got to C part 1 for error carried forward. Now again we've got a bit of infrared spectroscopy. An impure sample of C3H6O obtained by a student was analysed. Using that, the spectra contained an absorption between 1680-1750 and a broad absorption between 2550 and 3300 wave numbers due to the impurity. What does the absorption between 1680 and 1750 indicate? If you look at your data sheet, that is telling you it's a C double bond O, or you could also say carbonyl. And the broad absorption between 2550 and 3300 is an OH, but you cannot just write OH, because if it is a broad absorption in that wider range there, it is an OH from a carboxylic acid. That point needs to be made. So you cannot get the mark from just saying an OH, because that would be if it was an OH from an alcohol, for example, it would be less broad than that range given. And so our identity of our alcohol from A must be our propanol, but it's the reason that counts, and that is because we've got evidence of oxidation to a carboxylic acid. Remember, if it was a secondary alcohol like propanol, you would be getting a ketone. Final question. And lo and behold, we see yet again a question that gives us 2 types of structure to help us with our answer. We've got our structural formula and our skeletal formula. First point, asking you to name the 2 functional groups. Please note, it says name, and that means we cannot this time get away with the atoms and how they're joined. We have to say an alkene, so you can see our alkene there, double bonds, and also our alcohol, or they will accept hydroxy or hydroxyl as well. State which of the 2 functional groups you named is identified when bromine is added. Bromine, of course, reacts readily with an alkene, and more easily identified from the infrared spectra. I hope you're starting to realise that OH groups are really identifiable in the IR spectra, and so are alcohol. Both of those required for that 1 mark. What would you see when bromine was added to citronellol? is it decolorizes or goes colourless. Remember, discolours would not be acceptable, does not have the same meaning. Now, the skeletal formula of the organic product where bromine is added to citronellol, and it's asking you for skeletal formula. So, use this skeletal formula as our big clue. Here is the group that's going to react with it. Bromine is added, it reacts with the double bond. So pretty much everything else is going to stay the same. So I'm going to draw out the same backbone. Make sure we're putting our groups in the same place. Okay, so we've got our same backbone exactly as in our citronellol. Now where our double bond was here, that is where we're going to add across our bromine. And so we're going to need to put one bromine of that carbon and one bromine of that carbon. And there we have our correct structural formula, or skeletal formula. Remembering the bonds to the bromine should be exactly the same length as all the other bonds that you've shown. Finally, another infrared just to check your understanding. Make sure you've done this bit. Some people miss this one out. There's actually a mark available here because it's asking for a letter X on the absorption, confirming the presence of the functional group that's most easily identified from this spectrum. Remember, that is this peak here. This one here, if you've incorrectly identified that one is actually the CH. And that's not really a functional group at all, remember, because that's pretty much present in most organic compounds. And all of these over here, remember, we're not generally interested in many over here. That's what's referred to as the fingerprint region. So it's this one here, this left-hand peak, high up in the 3000s, that's our OH. Last question, in the reaction of C10H20O with hydrogen in the presence of a catalyst forms a saturated compound C. The catalyst, you should be recognising, reaction with hydrogen is a hydrogenation reaction, and the ideal catalyst would be nickel, but they will also accept platinum, rhodium or palladium. The molecular formula of the saturated compound C, remember this is an addition reaction. So all we need to do is we need to add in those two hydrogen atoms. So that formula can change to C10H22. So just adding 2 to there, and don't forget that O is still there. And constructing that equation, if we are starting with C10H20O and we are adding hydrogen H2, that is why we are forming C10H22O. It is an addition reaction, two things coming together to form one. Okay, and that is the end of our mark scheme. I hope if you did make any mistakes, you found me going through that useful.